Let's talk about gaseous systems in relation to equilibrium. And it turns out that one can write down a different sort of equilibrium constant known as the partial pressure equilibrium constant, otherwise known as Kp, for equilibrium gaseous systems. So we're talking about systems where all the components in that gaseous mixture at equilibrium are gases, all right? The expression for writing down the equilibrium constant under those circumstances is given right here. Kp is equal to the partial pressure of the gases that are products raised to their respective coefficient in the balance equation divided by the partial pressures of all the gases that are reactants, again, raised to their respective equilibrium constants, all right? So basically, that's the Kp expression. And it turns out that there is a relationship between Kp and Kc, and it is given by this equation right here. I could derive it and show you how it's obtained, but I won't. I leave that for you to figure out. Or if you have any questions, you can call me and let me know that you want to understand how these two are related. So this is the expression. Kp for the system is equal to Kc for the system times RT. R is a molar gas constant, which in this case is equal to, write it right here. The R here is equal to 0.0821 liters atmospheres over mole Kelvin. And T is the temperature in Kelvin. All right. And delta N here. Okay. Delta N here is basically, as stated here, the difference in the sum of the coefficients of the products minus the sum of the coefficients of the reactants, all right? So in this particular hypothetical example, delta N would be equal to G, lowercase g plus lowercase h, the sum of that, minus lowercase a plus lowercase b, and that is delta N, all right? So again, this underscores the importance of having a balanced equation, right? Because the balanced equation will give you the correct coefficients, and that is what is needed in order for you to write down the correct value of delta N so that you can properly relate the Kp value to the Kc value according to this equation. Okay, so that's basically some introductory comments concerning the equilibrium constant under for gaseous systems. So let's look at this example right here. So you're given this equation here, this balance equation, up here, and they gave you the Kp value, which is this, at 319 Kelvin. So the question is asking for the Kc value for the A part. So for the A part, they're asking for the Kc value. Now remember, from before, Kp is equal to Kc times RT raised to the delta N. So Kc, which is what the question is asking for, will be equal to Kp times RT to the minus delta N, right? So what we need to do here, let me erase this right here. Okay, so what we need to do basically from here is to plug the numbers in. So therefore Kc would be equal to Kp. Now Kp is given as 0.660 times R, which is 0.0821 times T, which is 319 Kelvin. And you'll notice I don't include the units here because if you recall, I told you that when it comes to the calculation of Kc or Kp, the units are not important, all right? So let me just work this out here. So 0.082, oh, I forgot, delta N. So delta N would be the difference in the coefficients of the products and the reactants. So the coefficient of the product here is 2. The coefficient of the product here is 1. So therefore, up here, I'm going to put 2 minus 1, right? Which is equal to 1. All right, so that doesn't change anything right there. So let me just do my calculation. 0.0821 times 319 raised to the 1 times 0.660. And according to my calculations, this works out to be equal to, round off to 363. So this would be 39.7. So the Kc value for this reaction is 39 point, hate when that happens, 39.7, all right? So that would be the Kc value, which would be the answer to the A part. Okay, now the B part is asking what is the Kp for the reaction of 2NO2 to form N2O4. So if you look at this equation here, you see that this equation for the B part is the reverse of the initial equation given, right? So what does that mean for the Kp value? It means that the Kp value for the new equation would be 1 over the Kp value for the initial equation. So therefore, B would be equal to 1 over 0.660. So let me do that here. 1 divided by 0.660. According to my calculations, this works out to be equal to 1.52. 1.52 is the answer. So that basically answers the B part. Okay. Now, the C part, it says, if the equilibrium pressure of NO2 is 0.332, what is the equilibrium partial pressure of N2O4? So I'm going to need some space to answer this one. So let me erase all of this here. Okay, so let me go back to my, okay, why is this thing? Okay, so the question gives you the partial pressure of NO2, right? And the question is asking for the partial pressure of N2O4. So for this expression here, we can write down the Kp expression, which is Kp is equal to the concentration of NO2 squared divided by the concentration of, shucks. This should be partial pressure, not concentration. I'm so used to concentration. Okay, so let me rewrite this here. It will be the partial pressure of NO2 squared divided by the partial pressure of N2O4. All right, so that's what Kp is equal to. This is Kp here, all right? So the question is asking for this, the partial pressure of N2O4. So therefore, the partial pressure of N2O4 will be equal to partial pressure of NO2 divided by the partial pressure of, divided by Kp, all right? And the partial pressure of NO2, of course, is squared. So all we have to do from here is plug the numbers in. So we're going to have 0.332 squared divided by Kp, which is 0.660. And that's it. So 0.332 squared divided by 0.660. Okay, so according to my calculations, this works out to be equal to 0.167. And that will be the answer for the C part. All right. Okay, so I'm going to stop here. And the next video we'll be dealing with the topic that you see on the screen, equilibria involving pure solids and pure liquids. Okay, until next time.